Moving on with our calculus, antiderivatives. In some sick, twisted way, this is my favorite part of calculus. Some of y'all will consider it your least favorite. I'm not sure. To me, they're almost like puzzles, but for now, they're going to be a little bit easy. Antiderivatives will start to get tricky. I don't know if you remember back in the day when we first learned derivative shortcuts, but we started off with this nice, cute power rule. And y'all said, wow, this is great. I love derivatives. These are wonderful. This is so much better than limits. This is the best thing ever. And my phone is ringing. And let me pause the video and stuff like that. All right. So anyway, see, when I pause the video, I come back. I'm so lost. I just lost all my flow. I was on a roll there for a minute. I was talking about something. Anyway, antiderivatives, much like derivatives, they're going to start off easy, and they will eventually snowball into more difficult things, as the same happened with derivatives. So now that I've given you a full 1-minute introduction to this, let's start talking about antiderivatives, which simply means I will give you the derivative, and now we work backwards to find the function. And so we're going to start off with something kind of nice and clean, like maybe f prime x equals this. If this is the derivative, what do you think the function was? And well, what it ends up being here, let's see, this is after I brought down the exponent, so what I probably have here is f prime. I don't want to write f prime because I'm finding the derivative, or the original function. Okay, so f of x, in this case, well, if I start with an x squared, the derivative of x squared is 2x, and the derivative of what would be 7? Well, I think it'd be 7x. The derivative of 7x is 7, so your function would be x squared minus 7x. So well, then let's try this one. It's x squared plus 3x. This one's going to be a little bit tougher. Actually, it's going to be maybe a lot bit tougher. So let's see, my original function. Well, if I have an x squared after the derivative, that means I had to start with an x cubed, because you subtract 1 from the exponent when you do the derivative. The problem is if I do the derivative of x cubed, that's going to give me 3x squared, but I only want 1x squared. So what I'm going to have to do is undo that 3 by dividing by 3. Then I would have 1x squared, right? So what our trick is to this one is it's x cubed, but then I'm simply going to divide it by 3. So now when I do the derivative, I'll bring down the 3. That'd be 3x squared over 3, and the 3's cancel. Once we have x cubed over 3 plus, and the derivative of 3x is going to be equally difficult. I probably put too much of a tricky one here. If you remember with the derivatives, I told you if you have a constant, you can kind of ignore the constant and do the derivative of what's left. I'm going to do the same thing here. I'm going to ignore the 3, and I'm going to do the antiderivative of the x. Well, if I was left with x to the first, that means I started with an x squared, but when I bring down the 2, I'm going to have to cancel it. So this is really tricky. I probably shouldn't put one this tricky or touchy-feely at the beginning. But we end up with 3x squared over 2, because when I bring that 2 down, it's going to cancel, leave me with only x to the first. And those are two functions. The derivative of these functions is 2x minus 7, or in this one, x squared plus 3x. We're going to come back and add just a little bitty thing to these problems to make it exact, but this is good for now. So that's finding antiderivatives. There is a notation for antiderivatives. And the notation for an antiderivative, meaning to find the antiderivative, is this elongated s. Technically, the s stands for sum, but that's not something you need to worry about right now. But so the antiderivative, that's what this symbol means, find the antiderivative of 2x. And the dx simply tells you what the variable is. I know that seems picky, and that's kind of a bad answer for now, but we'll just say dx tells you what the variable is. So this is saying find the antiderivative of my function 2x. Well, the antiderivative of 2x would be, the derivative of x squared is 2x, right? And the dx basically just tells you where the function ends. So I almost see the integral sign, or the antiderivative sign, as open parentheses, and the dx as an end parentheses, and you find the antiderivative of everything in between. And the same thing for number 4 down here. The antiderivative, and you heard me say integral a second ago. This is also called integrating. The antiderivative, the integral of 3x squared plus 7. Well, the derivative of x cubed is 3x squared, and the antiderivative of 7 would be 7x. And now I'm about to add something else to this, because some of y'all may be screaming, you know what? What if I decided to say my original function was x squared plus 6? If I take the derivative of x squared plus 6, well, the 6 goes away and you're still left with 2x. Well, what if I decided to make it x squared plus 64? Well, the derivative of 64 would go away, so this would still be correct. I could even say the antiderivative of x squared plus 64 e to the pi times the ln of 7, and any other constant I want to throw in there. You could put any constant right there, and the derivative of it would go away. So when we do antiderivatives, there is something called the constant of integration. And what we will do is we will simply put a plus c. And that plus c just represents any constant that you could have, because when you take the derivative, it goes away. So after every antiderivative, this is a general antiderivative, you put the plus c to represent that constant that would go away when you take the derivative. And that's what I want to add to these problems. We need to add a plus c, because if you take the derivative, any constant would go away, and this would still be correct. Right, so that's your brains behind antiderivatives. Let's do a handful of them. Oh, wait, I forgot. Before we do a handful of antiderivatives, there is a general formula for doing antiderivatives of this nature, just like there were general formulas for derivatives. If you are doing polynomials or anything that's basically the reverse power rule, it's almost like we are unpower ruling here. Basically, what we do is we do everything in reverse. If you think about derivatives, we brought the exponent down and multiplied, and then we subtracted one. We're going to do the exact opposite here. If it's x to some power, we will add 1 to the power instead of subtracting, and then we will divide by the new exponent instead of multiplying by the old exponent, which is what we did with derivatives. So we do everything in reverse. We add 1 to the new power and then divide by the new power. Some people like to write it this way. So for example, if I had the antiderivative of x squared, I would simply add 1 to my new power. To my old power, 2 plus 1 is 3, and I'll divide by that plus c. Or you could write it as 1/3 x cubed plus c. That is your general rule for finding antiderivatives of polynomial-like functions. Let's see, let's try one. X cubed plus square root of x. Well, square root of x, when I do the antiderivative, I'm going to do the same thing I did when I was doing derivatives. I'm going to change that to x to the 1/2, because I like to see that exponent. And I'll follow my rule. X cubed, 3 plus 1 is 4. Divide by the new exponent. Plus x to the 1/2. 1/2 plus 1 is going to be 3/2. Divided by 3/2. Plus some constant. And don't forget the plus c. Most people, from now on, the way I will write this one is, well, x to the 4th over 4 is pretty sexy. We'll just leave it as it is. But if you divide by 3/2, that's the same thing as multiplying by 2/3. So 2/3 x to the 3/2 plus c. And that would be our answer. For this one, kind of the same thing I did when we had derivatives. I'm going to see if I can clean this up. For number 6, we can actually do an STD here. We're dividing by one term, so I could say x to the 6 over x to the 4th. You know your STDs, right? Single term denominators. Got to split that up. 4x to the 5th over x to the 4th plus 1 over x to the 4th dx. And then we'll clean that up. X to the 6 over x to the 4th is x squared plus x to the 5th over x to the 4th. That'd just be 4x. That's actually minus 4x. And then 1 over x to the 4th, just like with derivatives, we have the same mindset. This is going to be a lot easier to do if you write it as x to the -4 instead of as 1 over x to the 4th. And now I can follow my power rule. Add 1 to the old power and divide by the new exponent. Minus 4, it was x to the 1st. We'll add 1 and we'll divide by the new exponent. And the 4 just comes along for the ride. All constants I'm just going to bring along for the ride. Plus -4 plus 1. Be careful with your negatives. -4 plus 1 is -3. Over -3 plus some constant. And I'm okay if you leave it like that, but if you're an overachiever, 4 over 2 is 2, and then that'll be what? I'm just going to leave it as x to -3 over -3. You could move that x cubed to the bottom. And I'm okay with either one of these two answers. Good, bad, ugly? Good, 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 good. How far have we gone? 10 minutes. Not bad at all. Not bad at all. Let's see. Number 7. Okay, right here we are multiplying. So that's a product, right? Right? There actually is a technique to undo the product rule, to do products backwards in antiderivatives. The problem is it's extremely tricky. So for problems like this, even after we learn all of our antiderivative techniques, I still would channel my Algebra 1 skills and multiply this out and simply do power rule. So that's going to be the same thing as x squared plus x minus 12. And then we'll follow the power rule. Add 1, divide by the new exponent. Plus, that's x to the first. If you add 1, you get x squared, divide by new. Minus 12x, the derivative of 12x is 12, and don't forget your constant. Yeah. So those were all antiderivatives of power rule stuff, polynomials, things that you can simply add 1 to the old exponent and divide by the new. Okay, then we're going to get into things like cosine x. And there are a lot of antiderivatives that you just need to recognize. There's really no techniques for solving it. You just look at it and say, oh, that's the derivative of something I know. And in this case, cosine, the antiderivative, some of y'all are screaming, it's sine, it's sine. And you have to be careful with cosine and sine. Let's see, if you're thinking sine, the derivative of sine is cosine, is positive cosine, so that would be correct, sine x plus c. The one that trips people up is if I ask for the antiderivative of sine x. Because people want to say the antiderivative of sine is cosine. The problem with that is that if you remember way back in the day, we learned our trig derivatives, or we were supposed to anyway. If I gave you cosine x for a function, the derivative of cosine was negative sine, not positive sine, which is what I want here. So the antiderivative of sine x is actually negative cosine x plus c. The antiderivative of cosine is positive sine x plus c. And that really trips people up a lot. So be extra mindful of whether it should be positive or negative when you're integrating your trig functions. Let's see, number 9, 1 over x minus secant squared. Now, secant squared should be easy, easy, easy. Why should secant squared be so easy? Anybody? Anybody? That's because you recognize that as the derivative of tangent x, right? Didn't you learn your trig derivatives? So secant squared is the derivative of tangent x, so that one's easy. The 1 over x throws people off because the first thing people want to do, I'm peeking into your brains, by the way. I have that ability. You learn how to peer into people's brains in YouTube. Something I learned. All right, 1 over x, what people want to do with 1 over x at the very beginning of antiderivatives is they're thinking, oh, I remember we did something like this earlier. I'm going to change it to x to the negative 1. And you're going to say, aha, x to the negative 1. I'm going to follow my power rule, negative 1 plus 1. And if you're really good with your addition, you know negative 1 plus 1 is 0. So you're going, aha, x to the 0. Beautiful, that's 1. Don't forget, you have to divide by the new exponent. And so you're saying, aha, x to the 0 over 0. And we run into a problem there because you cannot divide by 0. The world explodes and cats start sleeping with dogs. So that came out the wrong way. I meant as in like actually taking naps together. Quit being so, okay, whatever. So here we are. For this reason, because you ultimately end up dividing by 0, you cannot do the antiderivative of 1 over x this way. 1 over x is actually a recognition derivative. This one, what we just did was all wrong, so I'm going to get rid of that, pretend it never happened. 1 over x, if you're really astute, you recognize that, because that is the derivative of the natural log of x, right? 1 over x is the derivative of natural log x. Secant squared is the derivative of tangent. So this problem was straight up recognition. The antiderivative is going to be the ln of x minus tangent x. Don't forget the plus c. Now there is one little thing I'm going to add to this. And for now, just accept it as truth. We will explore this later in more detail. But if you do an antiderivative and your answer is a natural log of something, you always put the something in absolute values. The short reason we do that is just in the off chance that x is some negative value, it's okay for me to plug negative x's into my original function. So we have to consider the fact that x could be negative. So we put it in absolute values to fix that problem. So just know that if you ever do an antiderivative and your answer involves the natural log of x, you need to put the natural log, or the x part, in absolute values. All right, last one. 1 over 1 plus x squared plus sine x over cosine squared x. Now this is brutal, right? This just looks absolutely painful. And especially this sine over cosine squared, that is going to be painful. But this is beautiful. I love this. I love that antiderivative because I see that, and you know what I'm thinking? You know what I'm thinking? Because I actually studied and I learned all my derivatives. I know that that is the derivative of inverse tan x. So when I do this antiderivative, my first piece right there, 1 over 1 plus x squared, that's the derivative of inverse tangent. Now the tricky part is going to be the antiderivative of sine over cosine squared. We're going to learn some techniques later that we could use to solve this, but for now, we're going to have to play around with just some algebra and see if we can simplify this into something that's a little bit nicer. All right, so let's see how we can clean up sine over cosine squared. I'm going to come down here and almost create its own little problem. Let's see, sine x over cosine squared x. I know sine over cosine is tangent, but there's an extra cosine down there. So this is what we're going to do with this one. I'm going to turn cosine, and this is crazy, I hope this doesn't confuse you, into cosine times cosine. And if I do that, then I have the ability to say, all right, sine over cosine, actually I'm going to circle it a different way, and I have a reason for this. Sine over cosine is tangent, and if I take sine over cosine and turn it into tangent, I'm left with 1 over cosine, and 1 over cosine is equal to secant. So I can turn this into the antiderivative of secant x tangent x. And that, my friends, is a beautiful antiderivative because I recognize that. I know that secant tangent is the derivative of secant x. Yeah, so here I am. I'm just doing that separate little part, well, separate big part, on scratch paper. And so the antiderivative of sine over cosine squared turned into the antiderivative of secant x tangent x, which is secant x. So plus secant x for this red piece, plus t. And there's our answer for the antiderivative of all of that mess. So right now your antiderivatives are either going to be recognition or they're going to be power rule, but we will add to our techniques and muddy up the water a little bit later on in life.